right. What's up, Mistral? Hey, Sibley. Dun, 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 dun. Will the questions on this exam be similar to homeworks and to the clickers like the last exam? Yeah. Yeah, so I made an announcement yesterday on Brew and Learn, but yeah, expect this midterm coming up on Friday to basically be the same format, same everything basically as the first midterm, just the subjects change, right? We're not doing waves and fluids, we're going to be doing E and M. Yeah, that's really it. We're just doing E and M. Well, not M. We don't do any magnetism. That's 1C. So it's really just E. But electric fields, electric potential, capacitors, resistors, all that type of stuff. Oh, you're good. You just saw the announcement? Yeah. It's all right. Yeah, I put it out last night. It was pretty late. Let's see. Also in the announcement, I talk about the set surveys are now available. I think some people mentioned it on Campus Wire. They're like, oh, hey, you can go, like, review the class and stuff. And, yeah, I checked. I just got the notice myself on whatever panel I use for teaching. But this is what they have so far. So they say, could you open the last CUDA pre-lecture questions early? Oh, did I not? I'm pretty sure I did. Oh, I didn't. Oh, yeah, I said I did. I said I did, but I didn't. Yeah, let me do that. Sorry. I said I was going to do that. You know what? It's funny. I set the due dates correctly, but I just didn't make it visible. Okay, they're visible now. Yes, DC circuits is what we're going to do. Are we starting a new chapter today? We're continuing the chapter yesterday. Yeah. New chapter starts tomorrow. But on the exam, we'll only cover up to today. No stream on Twitch was lagging, Shantrix, unfortunately. I killed it pretty quick because I was dropping a lot of frames. I might start it again, but I don't know. But yeah, so if you're new to UCLA, there's this thing called like SET, Student Experience of Teaching, and the university uses it to kind of like analyze performance in classes and stuff. So it's really important if you fill it out, but we also give a little bit of an incentive if you fill it out. If 80% of the class fills out these reviews, which are due on the 29th, so that's soon. So that's a week from today, and it's at 8 a.m. really. So I don't expect people to really do it before 8 a.m. But if at least 80% of the class does this, then everyone in the class gets bonus points on their final grade. Will the final be 3 hours or 6 hours? The final, I'm shooting for it to be kind of maybe the same length as a midterm, maybe 2 midterms worth. And I haven't decided exactly yet. It's not going to be. We are scheduled for 3. The registrar gave us 3 hours technically, but this is an online class, so I can give you whatever time I want. I don't have to like rent a room out. The only thing is that we do have to start the exam when they say it starts. So I have to start it at 11 a.m. I'm leaning towards giving you 6 hours to do it, instead of like making everyone do it within the 3, because at least the feedback I got from the midterms is that it took you 3 hours to do a midterm because it's tedious. That exam is not very long. The midterms you should be able to do in like an hour and a half. I understand that the numbers make it annoying. And the reason we have to do the numbers being annoying is because it's an online class and cheating and whatever that, I don't know. Just all this stuff. So I'm leaning towards 6. Goat behavior. I appreciate. I'm always getting called goat. I think it's kind of cool. Anyways, yeah, y'all are at 20% so far, which is pretty good because I think surveys opened like yesterday. So awesome. You already got 20% of the class to fill it out. It's really easy. It's really fast. I think it takes like 5 minutes, but go do it. Everyone else in your class will be happy you did it because then everyone gets points. Are regrades available for the final? Probably. Well, yeah, there has to be at some point, right? Because Kudu does screw up sometimes, And so I appreciate everyone that we didn't have that many Kudu mess ups, like technically. I think there was maybe like 3 or 4 where, they said they submitted an answer, but it never got recorded. So it was pretty, considering that we have 120 people and then there's 10 questions on the test, it was pretty low to only have like 3 or 4 things really mess up. But, yeah, we will have regrades. I need to see exactly when the grades are due. They keep shifting the deadlines all the time. But the exam's on Friday, so I need to then get it graded probably by Monday, which is quite a feat for a final. And then I hope final grades aren't due until like the next week. Because if any of you guys are taking summer session, C? I think that comes up pretty quickly. That's like the week after. I think it starts or 2 weeks after. So... yeah, it says last midterm took me 4 hours. I'll make sure you have enough time for the final. Yeah. Maybe I'll make the final I haven't even written your other midterm yet. I'm still working on that. It's because I just finished grading the first midterm with all the regrades. But the final I will probably make longer than a midterm, but not obscenely long that you can't finish it. I think that's the worst thing when a professor gives an exam that you can't finish, because then you just feel bad. You're just like, I could have done this. I just need more time. That being said, it is, I can't give infinite time. You don't get infinite time on your work projects when you go into, I don't know, the real world in real life. There are deadlines, and so you have to get kind of good at doing things in a set time period. And the best way to do that, right, is with practice. So, but I'm not going to be unreasonable. Okay. Dun, dun. All right. Today's lecture, yeah, we're going to go over a little bit more on resistance and EMF, and then maybe we'll start dabbling into circuits. We're definitely getting into circuits tomorrow, and on Thursday. I say that I can solve it, but in reality, that is an excuse. Yeah. And then, yeah, next week, more circuits, and then probably a couple review lessons on kind of the harder topics that I didn't get to cover, just due to time. And then, yeah, all the homework's been released so far. Yeah, I think I just released it today. So there are no new assignments coming up next week. We will still have clicker questions next week. I might cut those on Wednesday, though. I might be like last clickers on Wednesday, just so that I can get final grades from Kudu all linked up to Brew and Learn, and then you know where you stand in the class. Because as of right now, the only thing I think in your grade is an exam and the discussion sections, which is only 20% of your grade so far. So the other 80% still needs to get put in. Okay. Any other questions? Feel free. Ask me during lecture, or throw it up on Campus Wire. Let's kick things off. Discussion isn't on there yet. It should be. I think there's some discussion on there for sure. Right? Some of the assignments should be there. I don't think I linked all of them yet, but some of them are there for sure. None of the clickers are. Nothing from Kudu is on there. Yours isn't? Oh, well. Someone else please tell me if theirs is there or if I need to go fix things. Oh, it's on Gradescope, but not on Brew and Learn yet? Really? 1 sec. I thought I put it on there. Oh. You know what? They are there, but y'all can't see it. That's what it is. Yeah. Okay. I see. Yeah, okay. I need to make it visible. Okay. Yeah. It's okay. I will do that. Yeah. Your grades are on there. You just can't see them. I will update that. But also I need to talk with Albert to see if he has all his discussion stuff on there yet. So the assignment exists, but the grade is unknown. Okay. It's okay. We'll get all final grade stuff. Don't worry about any of that until after the midterm. Focus on the midterm coming up on Friday. Next week, we'll get all your grades sorted out. And then you just prep for the final. Okay. Week 5, this is lecture 2. So, let's see. Yesterday, we went through a lot, actually. We went through like current. We went through resistivity. We went through resistance. Right. Now we can go through... we did a little bit of temperature dependent on resistivity. And yeah, I actually there's a clicker question I wanted to do on this one. I had to do this. Yeah, here we go. Because this has actually a pretty cool practical application to it. So we talk about how the resistivity of a material at a temperature T is related by this equation. And alpha for conductors is usually positive, which means that resistivity increases with increasing temperature. So it becomes more difficult to throw electrons down a wire as the temperature gets higher. And we talked about that's because you're making everything in the wire, including the protons and neutrons and whatever, to like vibrate more, and they kind of cause traffic so that the electrons can't carry current. Have you completed thermal physics? I don't think many people in this class have done thermal physics. That's, I think, is 1C. I think covers a little bit of thermo. Or it's a completely separate class. I don't know. But this does involve thermals, right? Yeah. So we talk about the temperature and the resistivity. The reason why this is cool is you may have noticed that different electronics and things have like temperature sensors. And you may be wondering, wait, how does this digital thing measure how hot it is in the air? The old school way of doing it, right, is with a mercury thermometer, which I don't know. Has anyone even like seen one of those before? I don't know. Yeah, you guys, if you guys use these before, I remember this being used on me when I had like a fever. They would put these things in my mouth and see, what temperature it was. Yeah, these are old school though, right? Everything, and what this does is literally just like heats up metal and it expands, and then you see like from a temperature. Yeah, you've seen it, right? Yeah, okay. But nowadays we use like digital thermometers for everything, right? So digital thermometer, which is something like this, right? These are much easier, right, to measure temperature. And the technology behind like how that works comes from this. And it's because resistivity of different metals is dependent on the temperature. So you get what's called like a thermistor, which is really cool. So let me get a picture of a thermistor. Yeah. So yeah, these thermistors, so they're resistors, such that depending on the temperature, their resistance changes. And then you can use like a computer board or something to measure that resistance, and then feedback like what the temperature is on something. So the whole concept of like a digital thermometer comes from this property of resistance changing with temperature. And so, yeah, this is how we like measure temperature digitally. And it's how we can get, temperature measurements really quickly. and really accurately. When you had that whole like that mercury thing with the actual physical thermometer, you have to kind of wait. You have to wait for the metal to like expand, and you have to wait for the temperature to transfer, or the heat to transfer to whatever the device. With a thermistor, it's pretty instantaneous. This is why you get things like thermopens, these like really cool meat thermometers that can tell the temperature within like a second. It's because they use this concept. Okay, so I'm gonna need to make this one. There's a clicker question on this one that I want to go over. Let me go pull it up. Lecture 19 clicker, correct. Yes, here we go. Make this visible. And make it due later. At 11:59. Okay. So let's go here. Refresh. Lecture 19. Clicker. Here we go. And then I need some answer choices for you. Here we go. We need that. And then I need this equation. Okay, cool. All right, so it says copper wire has a resistance of 0.5 ohm at 20 degrees Celsius, and an iron wire has a resistance of 0.525 ohms at the same temperature. At what temperature are their resistances equal? And then they give us some alphas here. So alpha for copper is 0.0039, then alpha for iron is 0.0065. So this is kind of cool. So bigger number for alpha, right, means that the resistance changes more with temperature. So iron is more sensitive to temperature changes than copper is. Okay. Now, resistance is related to resistivity, right? Let me see what I need to do with that. Dun, dun, dun. Right, okay. Yeah, so, and then we know that resistance is equal to rho L over A. Okay. But we're going to assume that as we change the temperature on these things, that the length and the area is not changing. So we're going to assume that this stays constant. In reality, the metal actually does like kind of expand a little bit, but I think we're doing it with such low temperature changes that we assume any change in the length and the area of the metal is insignificant. Okay, so we need the new resistance of copper, which the resistivity is basically the same thing as the resistance because this is a constant. And we're going to say that that's equal to its initial resistance, which is 0.5. And then that's going to be 1 plus alpha, which is 0.0039. And then T minus T naught. So this is like the change in temperature. Okay, cool. So this is going to be T minus 20. Usually when you're doing things with temperature, you always want to convert to Kelvin. The difference here is that anytime it's like a difference in temperature, because like 1 degree Celsius is the same change in temperature as 1 degree Kelvin, you're okay doing things in centigrade right now. But whenever you end up taking thermo or anything that's using like PV NRT, that stuff you need to make sure your temperature's in Kelvin, which you probably remember from like chemistry. Okay, so then rho of iron is equal to its initial rho, which is 0.525. And then this is 1 plus 0.0065 T minus 20. And we want to know at what temperature are these resistances equal. Okay. So, I mean, you just set these two equal to each other, right? So we say, okay, rho Cu is equal to rho Fe. When does that happen? So you get this is equal to this. Okay. And now we got to solve for T. This is just algebra. Let me see. Pull up my calculator. Okay. 0.5 plus 0.039 195 T minus 20 times 0.00195 is equal to 0.525 plus 0.00341 T minus 20 times 0.00341. Okay, this is just annoying with algebra. Because where's my thing with T? I just want this and this together. And then everything else will just add up and subtract or something. So, all right. Let's do this one. This minus my 0.00195. So that gets me 0.0014625 T is equal to, and then whatever happens with here. So here we go. 20 times 0.001925. Cool. 0.5 minus that. Exactly, Sib. Yep. Yeah, you're just finding what the new temperature is for each one with some new temperature T. Sorry, what the resistance is for copper, right? Based on its old resistance times, this is like the change that happens due to a change in temperature. And then you do it for iron, and then you set them equal to each other. 0.5 minus that. Cool. Minus 0.525 plus 20 times 0.00341 equals that, and then we divide that by 0.00014625. I probably messed up the algebra here somewhere. Okay, but I get T is equal to 2.87. Which is not right. Where did we mess up? Okay. Let me see. 0.0039, 0.0065. T minus 20, T minus 20. Yes. 0.5. 0.525. Yes. You know. I'm just going to put this in an equation solver. I'm not testing on you how to do algebra. Algebra just sucks. Oh, interesting. It's going to have to be a lower temperature. Oh. Okay. Actually, I was okay with my 2.87. I'm slightly off. Correct answer is 2.91. Okay, so t equals 2.91 is technically the correct answer. Which, yeah, there's probably just some rounding error in this. Okay, cool. Nice. Correct answer is B. That's interesting. I thought it would be a higher temperature. Just at first, I was like, oh, we must be going up in temperature, right? But then it turns out, right, that the copper wire has less resistance, and it also has a lower alpha, which means its resistance goes up slower with increasing temperatures. Yeah, why does that make sense, Sib? Good question. Okay, so let's remember, right? So that for metals or conductors or whatever. What? Reconnect, excuse me. What's going on with my internet today? Yep, that works. 1 sec. Okay. So for conductors, as T goes up, so does resistance, okay? But what we have here is we have copper at 0.5 ohms and iron at 0.525. This one has a bigger alpha. So alpha Fe is bigger than alpha Cu. And alpha determines how much the temperature goes up. Sorry, how much the resistance goes up as the temperature goes up. So this one is already higher. So as you increase temperature, it's going to get even higher than the copper does, because its gain in resistance is proportional to alpha. See how resistance is your initial resistance, and then basically times some alpha here. Well, it's 1 plus, and then, so it's always your initial resistance plus alpha times the change in the temperature. And if alpha is bigger, that means as temperature goes up, your resistance is going to go up even more. And copper is already behind. So at this point, you need to start lowering the temperature down, because copper is not as sensitive to temperature changes. So as you lower the temperature, the resistance of copper will go down, but the resistance of iron will go down even faster, because it's more sensitive to temperature changes. So eventually the lead that iron has enables it to come down and hit the same resistance that copper does as copper comes down as well. Does that make sense? Yeah, it has to do with like what the starting resistance is and then what the alphas are for each. If you're already behind, having a lower alpha doesn't mean that greater temperature will allow you to catch up with this. But if you're going in the opposite direction, if you're going down, that means a smaller alpha means you don't go down as quickly, so the iron will catch up on the way down fast as temperature drops. Yeah. Okay. Cool. All right. So how are these properties used for the utilization of the materials in science and engineering? Yeah, totally. So as I said earlier, you can use these properties to measure temperature of objects by just measuring what the resistance of the metal is in different situations. This also comes into play when you're developing high current wires and you want to know how much heat is going to be lost to resistance, and that heat being lost is now dependent on the temperature at which you're operating. So a thing here we see, right, is that for metals, as you go up in temperature, you get more resistance, which means you're going to lose electricity. You're going to lose power to the wire, to the resistance of the wire. And vice versa, if you lower the temperature, you lower the resistance. And this is where you get what are called like superconducting wires or superconducting magnets, or MRI machines, where you're trying to make really, really strong magnetic fields. To make really, really strong magnetic fields with wires, you need to run a lot of current through it. You're going to learn that in 1C. That's called, I think it's Lenz's law. But a lot of current creates a really strong magnetic field. However, if you're running a lot of current through a wire and there's any amount of resistance, you're going to start generating heat. And you start like melting and breaking things. So what MRI machines do is they run the electricity through their magnet wires at almost like 0 degrees. They use liquid helium to cool down the wires so that when they run the current through it, there is so little resistance that, you know, things don't melt. And this is also why MRIs are really expensive because you have to pay for liquid helium to cool down these wires. And liquid helium is not very cheap. We use it on like rocket ships and stuff. Let me see, like MRI machine, liquid. I'll show you guys. Yeah. So I don't know if you've ever been to an MRI, but yeah, they have liquid helium that they pump into these things to cool the wires down so the resistance is really low so that they can run a fuck ton of current through it and they don't break things. And this is also why that poor guy died. I think the other day or something, he got sucked into the MRI machine because he was wearing like a 20-pound chain for some reason. I don't know. But yeah, the magnetic fields created by MRIs are intense. They're huge. And you need a huge amount of current for that. And as I'm going to show in the next part here, if you have current and resistance, you start creating heat. It's like friction for electricity. A poor man's superconductor? Yeah. Yeah. Well, I mean, I don't know. The MRI is not... The hospitals are making fucking bank. They're okay. This is the reason why when... well, I don't know how much experience you guys have yet with the healthcare system. You're all probably pretty young. But as you get older and you want to get like MRIs for things because you're like, hey, I have a headache. Maybe I have a brain tumor or something. They usually hold off on ordering an MRI for you until they've checked all the cheaper options, which is usually a CAT scan or an X-ray. They'll do like other things that don't cost as much money because the MRI will end up costing the insurance company like thousands of dollars. Also, these machines are not cheap. I think to buy like an MRI machine, which some doctors end up doing, like as they get older, they start becoming businessmen. So they start like buying medical equipment and then like renting it out. But buying an MRI machine, I think, is upwards of a couple $1 million. So, yeah. Little thing. Little tidbit. Okay, cool. But yeah, great question, Sib. I like that you asked it. Like, yeah, why do we care about temperature dependence and resistance? And it's like, there you go. It's MRI machines. That's another really cool example. Okay. So let's see. Resistance, yeah. Let's get into Ohm's law. That's really the cool thing here. Yeah. So there are other ways you can use calculus to determine what the resistance is for materials. The example they do here, I mean, you should probably do this example at some point, but it's like for a coaxial cable. This is UCLA, yeah. The thing they do here, right, is that we learned that like resistance was equal to rho L over A, right? So it's like the length times the area. And then what they do here is they're like, okay, but let's say, for instance, that, you know, you have two different situations here. So you have like a center core of a coax cable, which is metal. Then you have like this dielectric insulator, and then you have a metallic shield, and then a plastic jacket. And here, I think they're trying to calculate the resistance of the whole cable. Yeah. Right. And the reason why you can't use this equation, R equals rho L over A, is because you have different you have different like areas, because you have like these concentrics, you have these donuts that keep forming. So what you have to end up doing is integrating from like some inner some inner radius to some outer radius, and then it's dr. But this, yeah, I see what happens here. Okay. Yeah. They go from here. Yeah. They're saying, for instance, if you wanted to calculate the resistance of the insulator here, you would have to integrate 2 pi r is equal to, right, the circumference of this like disk. I think this is called the Washer's method in calculus, right? And then the area, and then you're doing like dr. Yeah, it's 2 pi r L, and then dr is like expanding that washer further and further out. And when you do this, you get this classic answer. You'll see this a lot. You'll see a lot of like ln of like r outer over r inner or something. Yeah. This should say r inner, not r1. Man, I'm gonna spend August just going through this textbook and fixing all the errors. There's so many little tiny errors here. I'm like, what? But that's one way to calculate resistance with kind of a weirder geometry. So it's not just like a solid like cable where you can just say, oh, pi r squared times the length. This is the classic example, the easy equation we use. Okay. But where this all comes into play, and what we're really trying to like get to here, is dealing with Ohm's law, okay? Where Ohm's law says that the voltage and the current are like proportional to each other. So this is kind of the intro where they say I is proportional to V. And so what this means is if you have more current, you get more voltage or more potential difference through a cable. When we start thinking about resistance here, Ohm's law really just states that V is equal to I times R. So the potential difference across a component is equal to the current through that component times the resistance of that current, the resistance of that component. Okay. And then I talk about ohmic devices. I don't think we need to go over non-ohmic devices. That's just weird. Okay, the other thing that's cool here is going to be power. All right, we're going to talk about like, so Ohm's law relates V equals IR. Then we can talk about power, which is usually measured in watts, right? So power through an electrical component, P, is equal to I times V. So this is the power, and then this is the current, and then this is the voltage. You may have seen power when we talk about like light bulbs, right? Let's say, for instance, you have a 30-watt light bulb, okay? This tells you how much power the light bulb is emitting or consuming. And remember that power, right, watts, is also equal to like joules per second. Okay, so it's like a rate of energy. So if you had, let's say, a 30-watt light bulb, and let's say it was on a 120 volt socket, which is a standard American socket, is 120 volts. You can figure out the current that's required for this light bulb by just saying, okay, well, P equals IV. So 30 watts is equal to I, some unknown current, times 120 volts. Divide that, right? And you just get 1/4. So then I is equal to 0.25 amps. Okay. It's a very easy way to, if you see the power rating on something and you know what voltage it's being connected to, you can figure out how much current that's being drawn. Interesting thing, right? If you were in Europe, right, and you had a, let's say like a 230 volt line here, right, then you actually end up using less current in order to drive that same 30 watt light bulb. So this is usually like dictated by like the country you're in. I would say like country or, standard. And then the current is what changes based on like different things you're using. An example, right? Have you guys ever noticed maybe that if you use like a hairdryer or something, you end up like tripping a circuit? Let's see, what's like a standard hairdryer? Hairdryer wattage. I think a hairdryer is like 1500 watts. Yeah, there we go. 1200 to 1875. Okay, watch. So, for example, something more powerful like a hairdryer, which let's say is at 1500 watts. And the reason why a hairdryer takes up so much wattage is you're literally just discharging electricity through wires and getting the wire to heat up. And then once the wire heats up, you're like throwing air over it. So hairdryers are really electrically demanding because you're basically trying to break wire. You're just trying to heat it up so that it like glows. So you could do 1500 is equal to I times 120 volts. This is watts. Divide it, and then what do you get? You get like 1500 over 120. Cancel. 150 over 12. Ooh, what is that? Yeah, 12.5. Wow, that's big. Yeah, 12.5 amps. Look at that. That's huge, right? This light bulb took 1/4 of an amp to turn on a 30 watt light bulb, but a single hairdryer takes 12.5 amps. For reference, most house circuits or house sockets have either like a 15 or 20 amp fuse. And so what that means is if you draw more than 15 or 20 amps from that socket, it'll trip a breaker. And you have to like go find it in your house and you have to go like switch it and stuff. So you can see here, a hairdryer already like starts trying to really hit that limit pretty quick. So if you connected 2 hairdryers, you would 100% just trip the circuit. I don't know. I notice it in my apartment. If I run my air fryer, but then I'm also using my hairdryer, for some reason my bathroom circuit and my kitchen circuit are on the same breaker, it'll trip it all the time. It's because you're drawing too much current. And that comes down to looking at the wattage that different devices use. Yeah. Cool. The other way we can write this, right? So if we know that P is equal to IV, right? So another form. All right, let me put this on a different page here. So another form of power. So if you have P is equal to IV, but remember that V is equal to IR. This is, right, Ohm's law. You could substitute this in for V, right? So you could say this is also equal to I squared times R. Or if I rearranged for I is equal to V over R, now it's equal to V squared over R. So these are all equivalent statements for calculating the power of a device or a circuit. So you can either multiply the current times the voltage. If you don't know the voltage, but you know the current and the resistance, you can do I squared times R. And then if you don't have the current, you can just do the voltage squared divided by R. Good. Ask has a question, which says, so you can think of the current as the speed at which electrons travel across the potential difference. Correct. Yeah. Again, I like to think of it as a river. Voltage is like how wide the river is, and current is how fast the water is flowing. So if you have a bigger voltage, right, like a bigger, a wider stream, you can put more power down it. And especially if you have the stream moving quicker, which is bigger current, then you get even more power that's going down it. Yeah, voltage is kind of like just describing like what quality of electricity you have, right? Do you have a 120 volt line? Do you have a 240 volt line? You get to some crazy stuff with, if you ever get into like big power stuff, they have what's called like tri-phase 360, and that's like 360 volt lines. And then there's actually a cool reason why, for instance, we like to run high voltage lines across long distances, and it's due to the fact that you don't generate as much heat with high voltage as you do with high current. Yeah. Here, let me find that explanation real quick. There is a good one for it. Was it? Here we go. Yeah. So the key thing, this is a very important thing here, right? So power goes as I squared times R. So whenever we're trying to like transmit electricity from, let's say, like a power station to, like, let's say, like your house here, the cables they use will typically run at, these are like high voltage power lines. And the reason they do this is that the power lost in there being like some resistance. Again, remember, there's always some resistance in a wire, due to like there's resistivity, and then, you know, like how thin or thick the wire is. That power that you lose is proportional to I squared times R. So if your current doubles, the power you lose due to thermal heat in the resistor would go up by like a factor of 4. Versus if you want to still deliver power to a house, you can run the voltage really high, which means that your current will then be very low. And then now the power being lost through the resistor is going to be less. Or the power being lost through the resistance of the wire will be less, because this will go down. Yeah. So this is there's also arguments about like AC versus DC and stuff, but you don't get into AC circuits, I think, until 1C. So for now, this is all you have to know for power. Okay. And then, okay, I'll see if we'll get to cost of electricity. Let's see. There's, yeah, here, let's do another quicker question. This is a good one. Question 2. And then I see question 3's got some cool stuff on it. Okay, says, what is the resistance in a wire carrying 11.3 volts and a power of 4.63 watts? So this we can come from, right? Our P is equal to, we want just voltage and resistance. So that's this, P equals V squared over R. So for 4.63 watts equal to 11.3 volts squared over R, you can then solve for R. So this is going to be 11.3 squared divided by 4.63. And that's equal to 27.6 ohms. Not too hard, right? And that was answer choice B. Okay, but this is the cool thing I wanted to do. I wanted to do the lightning. Check the answer, please. Thank you. Yeah. So here we go. It says, what's the power of a 2.43 times 10 to the 8th volt lightning bolt having a current of 2 times 10 to the 4th amps? This is a lot, right? So in this case, right, power is just equal to I times V. You have the current, you have the voltage. So that's 2 times 10 to the 4th times 2.43 times 10 to the 8th. That's going to be a very big number. Okay, and that gets us 4.86 times 10 to the 12th. I think that's like a petawatt. I think, is 10 to the 12th peta? I think it's petawatts. Yeah. So, yeah, this is huge. But, one sec. Uh-huh. Yeah, 1 sec. What is 10 to the 12th? I think it's petawatts. That's 10 to the 15th. Oh, so it must be megawatts. No, megawatts is 10 to the 6. What's 10 to the 12th? No, what's the positive 12? Gigawatts. Is it gigawatts? Oh, terawatts. No, it's terawatts. Giga is 10 to the 9th. Okay. Okay, cool. This is terawatts, which is huge. Okay. So, that right here. And then I'm going to show some cool stuff about like where this energy goes. Okay, so this would be answer choice B as well. Because then we got to think about like what watts is, right? Cool. Okay, so let's kind of go back to this. So we know that 1 watt is equal to 1 joule per second, right? Watts is a unit of rate, okay? So if I wanted to figure out how much energy is in a lightning bolt, notice how that would be equal to power times the time, okay? Right? Because remember from mechanics, right? Power is defined as energy per unit time, or it's like work per unit time. Energy, work, all the same thing, yeah. So if we do power times time, you get the amount of energy. And then this is, right, this is measured in joules. So let's look up how much energy a lightning bolt delivers. Because, I mean, that is an insane amount of power. But lightning bolts are very fast. They don't dump that 4.86 times 10 to the 12th watts in a long amount of time. It only happens for a very short duration. So if we look up what's like the duration of a lightning strike. Lightning strikes last for microseconds. Okay, cool. So, I guess it's like times 10 to the minus 6 then? Yeah. I think I saw microseconds. Yeah, they definitely last less than a second. Okay. Well, let's assume it's just let's assume it's like 5 microseconds. Okay. Let's say lightning lasts 5 microseconds. Okay. So now the energy of a lightning strike would be equal to this 4.86 times 10 to the 12th joules per second, which is watts, times 5 times 10 to the minus 6 seconds. You can see how, right, seconds cancels out. So 4.86 e to the 12th times 5 e to the minus 6. You get, okay, but what's that in scientific notation? (2.43 times 10 to the 7). Okay. So that's 24.3 times 10 to the 6. Okay. So that's 24 megajoules of energy is in a lightning strike. You know, that's quite a lot, right? 24 megajoules. What's like a stick of dynamite? One sec. Energy in a stick of dynamite. Dynamite is around a megajoule. Okay, cool. So lightning in this case has the same energy being transferred as blowing up 24 sticks of dynamite. I think that's pretty cool. It's a pretty cool little calculation you can do. Nice. Okay. All right, let's talk a little bit about like power with like appliances and stuff. There's some practical uses to this. Okay, it says an ideal battery provides a voltage of 24 volts and delivers a constant current of 2.68 milliamps to an appliance. How much work does the battery do in 3 minutes? Ooh, okay. So work, right? This is kind of just asking energy, which we remember that energy is equal to power times the time. In this case, power for electrical things is current times voltage, and then we have the time here. So, and this is minutes. You don't want minutes, right? Everything needs to be in seconds. So that's going to be equal to 180 seconds. And then the power here, so you have 2.68 times 10 to the minus 3. That's milliamps. And you have voltage here, which is going to be 24 volts. All right, times 180. And then I'll show how this applies to, you've probably like bought power banks, right? Or portable chargers. They measure everything in like milliamp hours. We're going to show like kind of where that comes from. And then this times 180. So you should get 1.15 times 10 to the 1. So that's going to be 11. Now let's go back to regular mode. 11.6 joules. Okay, so looking back for our answer choices, that's also going to be, answer choice B. Cool. A lot of answer choice B's today. It says it's random. I don't know if that doesn't feel very random to me. Okay, so that's how you calculate the energy from a voltage and a current at a certain amount of time. Now, yeah, where this comes into play is a lot of times when we're saying the amount of energy being stored in something or the amount of energy being used, we're going to use the unit called like the watt hour. Or the same thing for this, right? If you want to talk about like thousands of watts that you're using, this is usually abbreviated like this, kilowatt hours. Okay. Remember this. This is right, joules per second times, some amount, 3,600 seconds. So what you end up getting is a unit for joules, but they will call that kilowatt hours. And it's related to how much power you are drawing from a thing times how much time that thing is drawing power. So let's take again the example of our hairdryer, right? So hairdryer ended up taking 1,500 watts, okay? And then let's say that we ran it, let's figure out how much, we can figure out like the cost of things, because this is what usually comes up on like a utility bill. You get charged by the kilowatt hours, which is similar to like when you have a water bill, it's like how much water did you use? How much water did you consume? Here it's how many joules of electricity did you use in your house or with your things. And they measure it in kilowatt hours, which it looks like a weird unit, right? Because it's power times this. We're usually used to things that's like meters per second or, or joules per second. Having like it on the top sometimes like confuses people. But yeah, it's kilowatt times hours, and that's a kilowatt hour. Let's see what like a kilowatt hour is in Los Angeles. Let's say LA County kilowatt hour cost. Okay, the average residential rate in LA is around 22 cents per kilowatt hour. Okay, cool. So let's say it's $0.22 per kilowatt hours. All right. So let's see how long I'd have to run a hairdryer. Let's have like an example here. How much does it cost to run a hairdryer? Let's say you use a hairdryer every day. So what? That's maybe 20 minutes a day. Let's say you use it 5 days a week. So in your country, it's 7 cents. Nice. Yeah. California is notoriously high. I think you pay even more when it's like during peak times. This is sometimes close to $1. Let's say the cost to run a hairdryer, let's say you're running it, let's say you use it 6 times a week, 10 minutes. So let's say you use an hour a week. Let's just say for a month. So a hairdryer for 4 hours. Okay. 1 month of using a hairdryer. Okay. Well, what you want to do is you want to figure out how many kilowatt hours that is. So I want to say, okay, how many kilowatt hours is equal to running 1,500 watts, but then you're running it at 4 hours, okay? So 1,500 watts, the power times the time, this gets you 6,000 kilowatt hours. And if 6,000 watt hours, 6,000 watt hours, which is then equal to 6 kilowatt hours. And if every kilowatt hour, good, thanks Roman, is 22 cents, right? That means this is costing you $1.32. So you say at like 22 cents per kilowatt hour. That's the cost to run a hairdryer for a month. So it's pretty cool. You can calculate what the different power draws are on different things in your house, and then how long they run, and then what the charge is, and then that's kind of what the the runtime cost is of using something. You'll see this if you ever go, again, you get older and you start buying like appliances. Let's say, for instance, I want, let's say like a refrigerator, right? Refrigerators are actually really cool because they don't actually run constantly. People think like, oh, is your fridge running? You might as well go catch it. I don't know. Refrigerators don't run constantly. They actually only power on like every couple hours to keep things cold. Good, we can talk about solar panels. Yeah, here we go. So here, for instance, this is an example. Is it more expensive to wash the dishes by yourself or to use a dishwasher? I think in terms of the environment, it is actually better for you to use the dishwasher, because most people, when they wash their dishes, just let the water run, and so you end up like wasting a lot of water. Whereas like a dishwasher is very efficient. It like only uses water when it needs to, and then the power usage is actually quite low. But for instance, you might see these tags. I think they're like federally mandated, you have to have them in the US. But if you ever see one of these tags when you're going to go buy something, do you see what it says here? Right? It says like, here's the estimated electricity use. This is on a refrigerator, I guess. And this is saying that you would use 150 kilowatt hours per year. And then they can put a cost to that, right? Now, you could figure out how many amps that thing is using, right? So, 150 kilowatt hours. I guess, well, here, it's actually really cool. Look, they talk about it here. They say, estimated based on 4 wash loads per week and a national cost of 14 cents per kilowatt watt. So that's not correct. in California, it would be more. Yeah. But yeah, I was trying to 4 wash loads per week. So what? That's 4 hours per week. Is a wash load like an hour on like this is a washing machine, sorry, not a refrigerator. So let's say 4 hours per week times 52. So that's like 208 hours, right? So if you do 150 kilowatt hours divided by 208 hours, now the hours are canceled, and you get how many kilowatts it's running. So 150, 123 divided by 208. So you get 721 watts. And remember that power, watts, is equal to I times V. And actually, so if you get a washing machine, usually you have to plug it into a separate socket, like a special socket in your house. And those things run at 230. They don't run at 120. So you do that divided by 230. And then that gets you 3. So I is equal to 3.13 amps. So that's cool. So from this, just this math here, we can determine how much current this washing machine is using. It uses 3 amps of current. And we just did it by like reverse engineering what they said like the yearly electricity use was. Yeah. You will see this also on like if you've ever seen like battery like portable chargers for your phone. So for instance, I don't know, if you go to like let's say portable battery charger for iPhone, right? They will rate these things in milliamp hours, which is weird, right? Because now this isn't watts. Now we're talking about like current times hours. Yeah. Or what's the standard one? The Apple one you guys have. Yeah, the MagSafe. What does this thing run? Okay. MagSafe. Here we go. So let's see like little tech specs on it. Course, classic Apple, they don't actually give you like useful numbers. They protect everything. Man, I want like the actual specs. Apple's the worst with this. Yeah, here we go. How many milliamp hours? Okay, there we go. This is actually terrible. What? 1460? This is classic Apple. They don't want you to know that this number is so low. 1500 milliamp hours? Bro, what? That's terrible. Most of these big chargers, look at this. This is 20,000. Okay, but let's say for instance, okay, the Apple charger. Yeah, that's hilarious, dude, that they hide that. This is garbage. This is absolutely trash. I wouldn't get a portable charger that's less than 10 10,000. This one's only 1,500. Okay. So 1,500, and then this is milliamps times hours. Okay. Now, this is the amount of current, and then this is the amount of time that it deliver. So for a standard, let's say, most cell phone chargers, or like most basic ones, will generate around 1 amp of current into your phone. So most phone chargers, I know there are some nicer ones that do 3, but let's say like it's just 1 amp. Okay. This is equal to 1,000 milliamps. Okay. So what this is telling you is that this Apple charger, which is 1,500 milliamp hours, is the same thing as 1,000 milliamps times 1.5 hours. This is also 1,500 milliamp hours. So this little Apple charger thing that you put on the back is equivalent to a standard wall plug, not a fast charger, a regular 1 amp charger running for 1.5 hours. I find it hilarious. What did they actually advertise on their thing, dude? I hate Apple, dude. They're the worst. I want to see how they were advertising this. Here we go. They say for up to 15 watts of wireless charging. So first of all, that's a rate. That's not the amount of energy. That's the rate at which it can deliver power. That says nothing about how much energy is in the power pack. Here we go. Yeah, where's this article? They don't actually say anything. Wow. Apple's the worst. Wow. Yeah. Yeah. Okay. The other thing you can see here, one last thing, because you were talking about, Sib, you're kind of talking about like solar panels and stuff. There is something cool with that. So let's do like an Anchor. No, I want Jackery solar panel combo kit or something. Yeah, here we go. Here we go. Yeah, like a portable power kit with a thing. Yeah. Okay, let's just see what this is. I want to show you guys how like the tech specs for this thing works. So this is you got to give me the specs on this. There we go. That's what I want. This is the cool thing that physics will allow you to. You can start deducing, which manufacturers are just lying about their products, because you can do the math and calculate. And then where's the solar? And then the solar panel is 100 watts. Okay, cool. So, and here they say the solar panel is 100 watts. Okay. So if we look at the battery capacity on this portable battery charger thing, so it comes with this, which is basically a big battery pack, and then there's a charger that's delivering power to charge that battery pack. They say that the battery capacity is 550 watt hours. Okay. So that's like half a kilowatt hour, right? Or so 20 cents in electricity. You can calculate, for instance, let's say I have my hairdryer, right? So my hairdryer was taking up 1,500 watts, okay? So I would need to multiply that by 1/3 of an hour to get 500 watt hours. So you can calculate how long you can run a hairdryer on this thing. You could only run it for 20 minutes before it would go away. Some things that are a little bit more efficient, right? I think I've seen like portable mini fridges. So let's say you're out in the wilderness and you want to like keep things cold. These are 12 volts. Where's like I need a Yes. So most mini fridges uses 40 to 60 watts for like the small ones. Okay. So if you're using, for instance, like a 50 watt, let's say like a mini fridge, then you could run this for 10 hours to get 500 watt hours. Okay. So it kind of shows this cool little inverse relationship between, right, wattage and how much time you can run a device. So you could run your hairdryer for 20 minutes, or you could run a mini fridge on this thing for 10 hours. Now, the power input going into this is only 100 watts. So if you wanted to calculate, for instance, like how much time to charge, well, the thing has a capacity of 550 watt hours. So you would need 100 watts of solar coming in for 5.5 hours in order to charge the battery back up. So yeah, and also this is assuming 100% efficiency, which is not true. I think most electrical things are 80% efficient, so with these power numbers, you actually have to add like another 20%, or like take 20% of the time out, because you lose energy due to heat with just trying to transfer electricity from like solar panels to a battery, or like from a battery pack to a hairdryer. You lose energy in the transfer process. But yeah, I hope maybe this helps you kind of see like the real world things of where like power, voltage, watts, watt hours, where this all comes into play, and use this to, you know, get a better feel for what is just like marketing garbage, and what's like the real the specs behind things. Yeah, they also talk about this. They talk about like, oh, something continuous, something surge. This is like instantaneous power you can deliver like for a short amount of time, and then this is like what's called RMS, which is continuous. Anyways, okay, we went a little bit over time, but okay.
My man.
I hope you guys learned some stuff from that. Again, I tried to go a little bit more into like the practical sense of things. Tomorrow we will start doing circuits, so we'll start seeing how voltage changes in different configurations of having resistors. We'll do some loop laws. We'll do some Kirchhoff, whatever you pronounce it as. And then also get ready for your test coming up. Cool. All right. We have office hours again today at 4 p.m. So that's in about 2 hours. So if you want to come by, ask some questions about homework stuff, clickers that don't make sense, please let me know. Roman says, do you think it'd be possible to achieve 90%? Maybe if you had a superconducting wire, like an MRI. But no, most electricity is capped at 80%. Yeah. Very welcome. Okay. All right. I will see you guys, if not at office hours this afternoon, same time and place tomorrow. Enjoy the